Good morning, everyone. My name is Alfa, and together with my teammate Anisha, we will be presenting our IoT fundamental case study entitled Child Proximity Alert System under the Safety and Security category. The objective of this project is to develop an IoT-based solution that helps parents monitor their children's proximity in crowded public places. Our system provides an immediate visual and audio alert whenever the child moves beyond the predefined safe distance. Next is for problem statement. In a crowded public places such as shopping malls, airports, theme parks, and a public transport station, children can easily become separate from their parents within a short period of time. This increases the risk of children getting lost or exposed to the dangerous station. Although GPS trackers are available, they often experience indoor signal loss, delayed location updates, and higher battery consumption. This limitation reduces their effectiveness in providing immediate alerts. Therefore, there is a need for an IoT-based children proximity monitoring system that can detect when the child moves beyond a safe distance and immediately notify the parents through local, visual, and audio alerts. Next is for proposed solution. To address this problem, we propose the Child Proximity Alert System, which is an IoT-based proximity monitoring system. The system uses a parent control unit based on an ESP32 microcontroller together with a simulated distance sensor. In our Cisco packet tracer implementation, contact thermometer is used to simulate the changing distance between the parents and the child. The parent control unit continuously monitors the simulated distance and compares it with a predefined safety threshold of 15 meters. If this distance exceeds this threshold, the system immediately activates a visual alert using an LED and audio alert using a piezo speaker. Although our implementation is a proof of concept simulation, it demonstrates how IoT technology can improve child safety through real-time monitoring and automated alerts. Next, I will explain the high-level system architecture of our child proximity alert system. This diagram illustrates how all the main components work together to monitor the distance between the parents and the child and generate an alert whenever the child moves beyond the safe range. Starting from the left side, we have the child unit, which represent the wearable device carried by the child. In a real-world implementation, this device continuously transmit a Bluetooth Low Energy or BLE signal that allows the parent's device to estimate the child proximity. The BLE signal is then received by the parent's unit, which is the main processing component of our system. Inside the parent's unit, there is a BLE module that receives the signal and send it to the ESP32 microcontroller for processing. The ESP32 continually calculates the simulated distance and compares it with the predefined safety thresholds, which is 15 meters in our project. If the calculated distance is less than or equal to 50 meters, the system considers the child to be within the safe range. In this situation, the LED and the piezo speaker remains off, and the system continues monitoring the child distance. However, the calculated distance is greater than 15 meters, the ESP32 immediately activates the alert system. The LED provides a visual warning, while the piezo speaker provides an audio warning, allowing the parents to respond quickly. On the far right of the diagram, we include an optional interface as a feature enhancement. In a real-world implementation, the system could be connected to a cloud platform such as Node-RED or Adafruit.io, allowing parents to receive notification on their smartphone and monitor the child location remotely. Overall, this architecture demonstrates how the child unit, parents unit, alert devices, and optional cloud service work together to provide a reliable IoT-based child proximity monitoring system. Next, I will explain the detailed data flow diagram of our child proximity alert system. This flowchart illustrates the sequence of operation performed by the system, starting from receiving the simulated distance value until the appropriate action is taken. The process begins with the distance sensor, which is represented by the potentiometer in our packet tracer simulation generation at the simulated distance value based on the child movement. This value is then sent to the parent control unit where the ESP32 microcontroller receives and processes the analog input. After that, the microcontroller reads the analog value and compares it with the predefined safety threshold of 50 meters. At this stage, the system makes a decision. If the simulated distance is greater than 15 meters, the system considers the child to be outside the safe range. As a result, the LED turns on to provide a visual warning, the previous speaker turns on to provide an audio warning, and the parents is alert immediately. On the other hand, if the simulated distance is 50 meters or below, the child is considered to be within the safe range. Therefore, both the LED and the piezo speaker remains off, and the system continues monitoring the child distance continuously. The discussion-making process enables the system to provide immediate alerts only when necessary, helping parents respond quickly whether the child moves beyond the safe distance.
Now I will demonstrate the manual override of our system using the emergency push button. As you can see on the screen, even though the child's simulated distance is currently safe, an emergency situation requires immediate action. By holding down the ALT key and clicking this red push button, I am sending a digital high signal directly to port D2 on our parent control unit. Instantly, the system bypasses the distant threshold logic. The microcontroller executes the override branch, forcing both the visual LED alarm and the piezo audio speaker to activate. This real time test confirms that our manual panic trigger works perfectly under proximity condition, ensuring maximum safety. Now, I would like to explain about our programming logic and loop. To explain our programming logic, we look directly inside the parent control unit's programming tab, where our script runs continuously without the loop function inside the main JavaScript file. Unlike setup configuration that run once, this function repeats indefinitely every 200 milliseconds to keep the system active. Next, the loop executes our entire safety sequence in four clean steps. First, it reads the sensor input from analog pin AO to calculate the child's distance. Second, it compares that value against our 15-meter threshold while checking the emergency button state. Finally, based on that continuous evaluation, the function directly controls the LED on digital pin 4 and controls the piezo speaker on the digital pin 5, which instantly toggling them to high activate the alarm during a breach or low to remain silent when it is safe. Next, I will present our sample log data. As we showed in the table, this dataset maps out the precise behavior of the child proximity alert system under different simulated distance values. Looking at the first two rows, when the child is within a close range of 5 to 10 meters, the system remains completely secure. The LED and piezo speaker are off, and the system status registers as safe. A critical boundary condition occurs exactly at the 15-meter mark. Here, the system status flags as an early alert state, though the physical actuator remain temporarily off because the distance has not yet strictly exceeded our boundary threshold in the code logic. However, once the simulated distance reaches this limit, reaching 20 and 25 meters, the parent control unit fully triggers the alarm system. As a result, both the visual LED and the audio piezo speaker switch to on to provide immediate tracking notification. This data clearly confirms that our system has successfully captured and distinguishes parameter changes in real time. Next, I would like to highlight the main development challenges we encountered during this project. The first one is packet tracer environment limitations. Because the software environment lacks native support for true Bluetooth hardware architectures, deploying an authentic wireless connection that wasn't possible for us. To we overcome this for proximity simulation. We adapted our approach and used a physical analog potentiometer. This served as an abstract substitute to successfully replicate and test our boundary logic without real-time RSSI signal strength tracking. We have come up with three future enhancements. The first one is we plan to implement true GPS integration to provide real-time location mapping on a parent's smartphone when boundaries are breached. Second, we aim to develop a dedicated mobile application capable of delivering push button notification and also vibration alerts if the physical buzzer is too distant to be heard by someone. Finally, we will add multi-device support, allowing a single parent unit to instantly monitor multiple children from a single interface. In conclusion, our project, which is Child Proximity Alert System, successfully demonstrated how IoT technology can improve a child's safety by providing real time monitoring and also automated alerts. Although this project is a proof of concept simulation, it provides a strong foundation for future real world implementation. Thank you.